Start. Today we are going to study about heterocyclic compounds. But first, in order to understand heterocyclic compound, we have to understand a term that is carbocyclic compounds. Now the carbocyclic have two things: carbo, that came from carbon, and cyclic. From cyclic, we are referring to the compounds which have a ring structure. So carbocyclic compounds are those cyclic compounds whose ring structure is made up of carbon atoms only. So for now, carbocyclic compounds are those compounds which have a ring structure made up of only carbon atoms. Now comes the term heterocyclic compounds. Now heterocyclic compounds, this term have hetero plus cyclic. Hetero is a term used for different kind of things if present in a system, like heterogeneous solution, homogeneous solution, heterogeneous solution. So those solution you understand. Similarly, heterocyclic compounds will have two different kind of things in it at least. So the definition can be: heterocyclic compounds are those cyclic compounds in which they have at least one other element in their ring system other than carbon atoms. Or in other words, we can say, if the ring system is made up of carbon atoms and at least one other element is present, the compound can be classified as heterocyclic. Alright, now the most commonly found heteroatom can be nitrogen, oxygen, sulfur, phosphorus, arsenic. So here we have example of both the thing, carbocyclic compound as well as heterocyclic compounds. This is benzene. In benzene structure, we have 6 carbon atoms present. Only the carbon atom forms the ring structure. So it is a carbocyclic compound. Here we have one heteroatom, that is X. It can be nitrogen, oxygen, or sulfur, or phosphorus. So this compound comes into the category of heterocyclic compound. Alright. Now classification. Classification can be based on the number or nature of heteroatom present, or degree of saturation, or size of the heterocyclic compound. Now, if we have a nitrogen heteroatom, then those compounds can be called azoles. If we have sulfur, then they can be called thiophenes, and similarly, so on and so forth. Second classification is based on degree of saturation, and it can classify in two ways. One, we can say saturated compound or unsaturated compound. Alright. Or we can also add one more thing, that is semi-saturated. It is not completely saturated, it is also not completely unsaturated, but some parts it have saturation, other it have unsaturation. So we can use the term semi-saturated. Alright. Other classification based on the saturation only is aromatic and non-aromatic. Now, what is an aromatic compound? For aromatic compound, there are two conditions, that is, a compound should have 4n plus 2 pi electrons and in conjugation. Alright. So that way we can classify the heterocyclic compounds into aromatic and non-aromatic. Third is based on the size of heterocyclic compound. Now, heterocyclic compound can have a ring system made up of number of atoms ranging from 3 to 10. Other classification can be simple heterocyclics or fused ring system. From simple heterocyclic, I refer to this heterocyclic compounds which have only one single ring present in its structure. For example, pyridine. What is the structure of pyridine? Now, in the previous slide, if we say that this X is nitrogen, then the structure will be pyridine. Alright, so pyridine is a simple heterocycle. Now, what are fused ring system? Now, fused ring system are the systems in which there are more than one ring fused together. I'll show you the example of fused ring system in the next slide. Here you can see indole. There are two rings that are fused together here. So this is an example of fused ring system. Another example, you can see quinoline, another one isoquinoline, and purine. Purine you must have studied in your DNA study. DNAs you must have studied the base. So this is the purine, this is pyrimidine. So pyrimidine is a simple ring structure, simple heterocycle, while purine is a fused heterocycle. Now these are the example of some of the heterocyclic compounds, and the most commonly known application of these heterocyclic compounds are in medicine. Allopathy medicines have the application of these. Now, pyrrole. The first compound we will be studying is pyrrole. Pyrrole is a 5-membered aromatic heterocyclic compounds, and also it is an azo compound. Alright, so the property of pyrrole will be the first thing that we will be studying. It has 3 basic properties. It shows aromaticity, it shows tautomerization, and it shows hydrogen bonding. For aromaticity, it should fulfill the condition of Huckel rule. What the Huckel rule says, it should have 4n plus 2 pi electron. Let's see how many electrons it have. So here we have 2 double bonds and 1 lone pair. In total 6 electrons. Or from this structure you can clearly see 1 electron present in the unhybridized orbital of carbon atom, and similarly all 4 carbon atoms have 1 electron in its unhybridized p orbital, which is perpendicular to the plane of the compound. And now carbon also have an unhybridized p orbital, but it have a lone pair. So in total we have 6 pi electrons, and all these unhybridized p orbital are perpendicular to the plane of our compound, and all of them are parallel. Alright, so there can be an easy overlap between these pi electrons resulting into the conjugation. So we can say this is a aromatic compound. Now we'll see aromaticity in this. What it says, pyrrole has 4 carbon and 1 nitrogen. All of them are sp2 hybridized, that we can see clearly. sp2 hybridization is planar, so our pyrrole ring structure is also planar. Now each ring atom contains unhybridized p orbital that is perpendicular to the plane of sigma bonds, or we can say plane of ring. Here p orbital are parallel to each other, so overlapping between p orbital is possible. Now non-bonding electrons are 4 from carbon, 2 from nitrogen, so in total 6 electron, and these 6 electron follows the 4n plus 2 Huckel rule, and they are also present in the resonance, or we can say they have a conjugation. So our pyrrole compound is aromatic. Now comes the second property, that is tautomerization. All of us know what is a tautomerization. It is shifting of a hydrogen atom, and it is 1,3 migration. So what is happening? There is a kind of shifting between your pi electron and hydrogen. Hydrogen is migrating to the third position, and our um, pi electrons, which are being shared between these two carbon atoms, will shift and will be shared between the nitrogen and carbon. So what is happening? This hydrogen is being released from here, and it is going on this carbon, and this pi bond is shifting from here to this bond. So we'll get this structure. Again, the hydrogen from here will shift here, and the pi bond will shift here, and we'll get this structure. So we have 3 structure of pyrrole in total. So it shows rapid migration of hydrogen from nitrogen to carbon. Now comes the hydrogen bonding. What is hydrogen bonding? It is a bond formed between hydrogen bond that is attached to a highly electronegative atom and another atom is a highly electronegative atom, and that atom could belong to the same compound, or sorry, I can say same molecule or the other molecule. And if it belongs to the same molecule, it is called intermolecular hydrogen bonding. Another was intramolecular. So what do we have here? This hydrogen bonding we can say is similar to the water. Nitrogen atom have a hydrogen atom bonded to it. Nitrogen is an electronegative atom, so it will attract the bonding electron of this bond, NH bond, towards itself. This hydrogen will have partial positive charge. Since it's positively charged, it will try to stabilize it by bonding with a highly charged atom. So that atom can be nitrogen atom from the another molecule, or it can be the pi electron system, that is pi bond, or you can say electron cloud of the pi bond. So there can be 2 type of hydrogen bonding possible in the pyrrole. One where hydrogen is bonding to the nitrogen of another molecule, and second one where hydrogen is bonding to the pi electron of the other molecule. Now here it is written as rise in boiling point. Every one of us know that water have a high boiling point as compared to its subordinates because of the hydrogen bonding. So similar thing is happening here. Now I would like to ask you a question. Think why can you explain which of the following will have high boiling point? Water molecule or pyrrole, and why? Alright, I'll leave this question to you. You think about it. In the next discussion class, you explain me the answer. We'll discuss this. Alright, now comes the synthesis. Synthesis of pyrrole is done by many methods, and we will be studying 3 methods. So the first method we will study is industrial process. In the industrial process, we have synthesis on a very large scale, so we have to consider a lot of factor: environmental condition, condition required for the reaction, some things changes from a laboratory reaction to the industrial process because the amount is changing. In laboratory, you do an experiment on a very small scale in milligrams, in grams, but in industries the same production is done on in tons. So you can imagine how um, exponential can be the effect of the things we neglect in our laboratory synthesis. So here comes the first synthesis, that is industrial process. In this process, what we do, we take our furan and we pass it over ammonia or a primary amine in the presence of alumina and at a high temperature. Here alumina is the catalyst with the formula Al2O3. What happens here? Here the water molecule is eliminated and instead of that NH group is attached here. That's the primary amine. Then we will have a substituted nitrogen in the Pyrrole. Second synthesis is Paal synthesis. In this we have 1,4-dicarbonyl compounds which react with ammonia or primary amines and results in the formation of pyrroles. Here the term pyrroles represent a class of pyrrole substituted molecules. It's not the pyrrole. It's not this pyrrole structure. It is actually a class of substituted pyrrole compounds. Now here also 1,4-dicarbonyl compounds. 1,4-dicarbonyl compounds are those carbonyl compounds in which they have two carbonyl group at a distance of 2 methylene groups, or in other word I can say they will have 2 methylene groups present in between the two carbonyl groups. So what is happening here? Here we have a 1,4-dicarbonyl compound and it has 2 methylene groups at its terminal ends and it is reacting with the primary ammonia. 2 water molecules are released and it forms a substituted pyrrole. In the mechanism, the first thing is nucleophilic addition. Your amine nitrogen will attack on the carbonyl carbon and it will get substituted here. Then imine formation occur, then dehydration occur and it results in the formation of pyrrole. Now let's see the let's see the mechanism. Here in the mechanism we have RNH2 which acts as a nucleophile. This nitrogen atom has a lone pair. So it is nucleus loving. It has high electron density over it, so it would like to react with the nucleophile. Sorry, not a nucleophile. It would like to react with something that have low electron density. So in the carbonyl bond, you can see the oxygen is more electronegative, so it will attract the bonding electron cloud toward itself. So carbon will have slightly positive charge. So this highly electron rich molecule will attack on the carbonyl carbon and this bonding electron, the pi electron, will completely shift toward the oxygen. So now here in the structure you can clearly see your oxygen will have a negative charge and your nitrogen will attain a positive charge because it is forming 4 bond, but charged species are not stable. So what it will do? It will lose 1 proton to stabilize itself. So that proton is lost and that proton through the solution will go to O negative and form OH. Hence, the positively and negatively charged species here become neutral. Now again nitrogen have one lone pair. Again it want to stabilize itself. So it will attack on carbonyl carbon again. Similar process will occur and again nitrogen will bond to the carbon containing OH. Still this nitrogen is not satisfied. What it will do? The lone pair again goes and end up removing OH. What will happen? This nitrogen will form a double bond with this carbon and OH negative will be removed. This nitrogen again will have a positive charge. In order to stabilize this positive charge, this molecule will lose this proton and these electrons will form a double bond here and these will go back to form a lone pair. So again nitrogen have a lone pair. This is a big issue. This lone pair will again go and remove OH negative and it will have a positive charge. Again to stabilize this positive charge, this proton will be lost. This electron will form a double bond here and these sigma electrons will shift to the nitrogen and again give it a lone pair. Now we are back to the square one. Nitrogen again have a lone pair. But is it satisfied this time? Yes, it is. How? Because this structure have 6 pi electrons in conjugation and that satisfies the 4n plus 2 pi electrons in conjugation, which is a condition for Huckel's rule for aromaticity. So now this compound has become aromatic and the lone pair of nitrogen is at peace at last. So the final product will be this. Now we were saying there are 2 water molecules lost here. Now see where those 2 molecules were lost. First one here where OH negative bonded with hydrogen form water. Another one here in this step, one OH negative was removed from here and hydrogen was removed from here. So another water molecule. So we can say 2 water molecules are released. Now I have a request to you. What you will do? This mechanism is very easy and I hope you understand it also, but you will write it down in your notebook all by yourself just for the practice and to check whether you understood each and every step in this or not. Now comes the second synthesis, Hantzsch's Pyrrole synthesis. What does this synthesis do? It's a reaction between alpha haloketones and beta ketoester. Now, alpha haloketones. This is the ketonic group. So this is the alpha carbon and the second here this carbon is beta carbon. So it has a halogen group or we can say chlorine at the alpha position. So this compound is alpha haloketones. Now another one is beta ketoester. This is ester group. This is alpha carbon. This is beta carbon, and it has a keto group on the beta carbon. So it is beta ketoester. Now both of these reacts in presence of ammonia and results in the formation of pyrrole. Now what does the mechanism say? What happens is ammonia again being nucleophilic will attack on the carbonyl carbon. Now this O will become O negative and your ammonia will have a positive charge. In order to stabilize both the charges, nitrogen will lose a proton. That proton will in turn attach to your OH. and again the stabilization process will occur, and this nitrogen again use up hydrogen and it will have double bond. And then tautomerization occur, enamine formation occur. So by reaction of your activated ketone and ammonia, you will get an enamine. In the next step, what happens? This double bond of enamine will attack on the carbonyl carbon, and this lone pair will facilitate this. And how? This lone pair will shift on this bond. It will form a pi bond here between carbon and nitrogen. So the carbon don't need this bond. So this bond will break, and that electron pair will attack on the carbonyl carbon and form a bond. This carbon will become a negatively charged. Now what happened? It is OH. Sorry, O negative. The protons will come. Proton will come from the solution and they will bind it. Or you can say that proton can come from here, because this nitrogen will become positively charged, and in order to stabilize itself, it will lose a proton. So that proton will bind to this oxygen, and some can come from solution, and this will release as water. And what will facilitate the release? Again, here is a proton atom present. That proton atom will facilitate, and a photomolecule will release from here, and we'll have a double bond here. So from the color, you can clearly see this structure is from alpha halo ketone, and this structure is from ketoester. So this we got a double bond here. Now again nitrogen have a lone pair of electron. So what it will do? It will again attack the carbon, the one carbon that is electron deficient. Here chlorine is a highly electronegative atom. So it will attract the electron pair to itself. This carbon will have a slight positive charge, and this lone pair will attack here. The chlorine will be released and a bond formed here. Now the bond is formed, but the problem is this nitrogen atom is again positively charged. So in order to facilitate that, a proton will release from here, and this double bond will be cleaved. How? The proton will be released, the electron will form a double bond here, this double bond will shift to the next bond, and this this pi electron will shift to the nitrogen, and it will neutralize the positive charge. So we got a substituted Pyrrole in Hantzsch's Pyrrole synthesis. Fourth synthesis is Knorr synthesis. What happened in the Knorr synthesis? Instead of a alpha halo carbonyl compound, here we have alpha amino carbonyl compound. What was happening in the previous reaction? We had a alpha halo ketone, we have activated ketone, and we have ammonia. So three different reactants were reacting together to form a product. Here what they have done, instead of this chlorine, they have taken NH2. So half of the work is already done. Now they will have to just react these two reactants. So what is happening? Condensation of alpha amino carbonyl component with second component containing an electron withdrawing group. That electron withdrawing group will be this, an ester, alpha to the carbonyl compound. Alpha is this electron withdrawing group will be attached on the alpha carbon. So This is the reaction. Here also two water molecule will be released, and how you can see here, this NH2 is a nucleophile. It will attack on carbonyl carbon. Again similar kind of process will occur, similar to the previous mechanisms we have studied. So NH2 will have a positive charge. It will bond to this carbon. This carbonyl oxygen will become to O negative. Now in order to stabilize this, NH2 positive will release a proton. That proton will go to O negative and form OH. Now again the same situation. Nitrogen have a lone pair. That's a very big problem. This will again try to stabilize itself by losing the proton and forming a double bond here, and in turn losing OH negative. So one water molecule is released, hydrogen from the nitrogen, substituted hydrogen, and OH negative from this carbon will release and form a water molecule, and we will have a double bond between nitrogen and carbon. Again this proton will be released, and there will be shift in pi electrons, and this nitrogen will have a lone pair. Alright, now what happens? This nitrogen will not attack anything. There is too much strain, so it will not attack the carbonyl carbon. Instead, this pi electron cloud will attack the carbonyl compound, or you can say this carbon will attack the carbonyl carbon with the help of lone pair of nitrogen. How? This lone pair will shift and form a pi bond here. This pi electron cloud will shift on this carbon, and this carbon will be highly electron rich, and it will attack on the carbonyl carbon. This carbonyl carbon is electron deficient, so it will form a bond. Very simply, electron rich and electron deficient species will form a bond. But, and there is a big but, this nitrogen became positively charged. It again wants to stabilize itself. So what will happen? Again a proton will be released. There will be shift in the electrons here. Pi electron bond will be formed. These pi electron will shift and stabilize the positive charge on nitrogen. Now what is happening? This OH negative and one hydrogen from this position will be released, and you will have an aromatic compound. And this release is very much similar to the previous reaction. So in the Knorr synthesis, what is happening is two water molecules have been released, and we are getting a substituted Pyrrole. Now comes the reaction of Pyrrole. So the first reaction that we will be studying is electrophilic substitution. What is electrophilic substitution? When an electrophile comes and substitute a group from the compound and attach itself, it is called substitution reaction. Now here it is written Pyrrole undergoes electrophilic substitution reaction at second position. So the second position is, this is carbon 2, this is carbon 3. Numbering is started from the nitrogen atom 1, 2, 3, 4, 5, or you can say 1, 2, 3, 4, 5. Or an alternative way of numbering is 1, 2 and 2 dash, 3 and 3 dash. So what is happening here is, we have an electrophile. That electrophile can come and break this pi bond and get substituted either on the carbon 2 or carbon 3. So let's suppose it gets attached to the carbon 2 position. What we will have? This carbon will have an electrophile, and since this is electron deficient species, so this carbon will have a positive charge. Alright, if it has positive charge here, it will try to stabilize itself. How it will stabilize? It can stabilize itself by the help of resonance. Now, this pi electron and this positively charged carbon that is on the third position can resonate. This pi electron will shift here, so this positive charge will be neutralized, but here this carbon will have a positive charge. Now this nitrogen have a lone pair. This lone pair will shift and form a pi bond here. You can see clearly in this structure it is forming a pi bond here, but now the nitrogen is positively charged, and this cycle will continue similarly. So what do we have? We have three resonating structure in the case when our electrophile is getting attached to the carbon 2. Let's see the case of carbon 3. If the electrophile attached to this carbon, what you will have? You will have a positive charge here. From this picture you can clearly see this carbon have a positive charge, electrophile is here. Now our lone pair can shift on this side. This positive charge will be neutralized, but positive charge will generate on the nitrogen. Now, can this positive charge further resonate? No, this nitrogen cannot form that kind of bond. So this positive charge will remain here, either here or here. So we will get only two resonating structure in the case of carbon 3. Now two reasons has been given in the explanation why pyrrole undergoes electrophilic substitution reaction on the carbon 2 position. First reason is C2 attack give more resonance contribution structures than C3. Extra stable contributing structure generates upon C2 attack. Now what it means from extra stable contributing structure? Now in the rules of resonance, there is a one point which says the negative charge should be present on more electronegative atom, and the positive charge should be present on the less electronegative atom. So here what we have? Now comes the electrophilic substitution reaction, and from this we can clearly see the resonance energy of the two resonating structure formed, one in the carbon 2 attack, another one in the carbon 3 attack. Clearly from the energy diagram we can see the resonating structure formed in the carbon 3 attack is having more energy, so it is less stable. Now comes the reaction. First is our pyrrole is reacting with nitroacetic acid, acetate and nitric acid. This acetic acid and nitrate form this kind of a structure which further react with the pyrrole and gives us a substituted pyrrole, and the substitution occur at C2. So what we have nitro substituted pyrrole. 2 nitro 1H pyrrole. Now if we react pyrrole with SO3 and pyridine, this will result in the formation of intermediate of this kind, which will result in the formation of carbon 2 substituted pyrrole, and substitution is SO3H. Now halogenation, or we can say chlorination. So again chlorination will happen on the carbon 2. If we react acetic anhydride in the presence of PF3, the CH3CO group, or we can say acetate group, will bind at the carbon 2. Second reaction is reduction. Again we are reacting pyrrole with acetic acid in the presence of zinc at room temperature. What happened? Reduction occurs. The double bonds are reduced and hydrogen gets attached there. So in case of zinc and acetic acid, partial hydration occurs. 2,5-dihydropyrrole forms. In case of platinum and H2, complete hydration occurs and we get pyrrolidine. That is Riemann-Dimer reaction. What happens in the Riemann-Dimer reaction? The Riemann-Dimer reaction, your pyrrole reacts with CHCl3, that is chloroform, and KOH. KOH is a base. And in this reaction, a nucleophile CCl2 is generated, which attacks and get bounded on the carbon 2. But this carbon doesn't fulfill its valency, so it will take water molecule from the solution and it will result in the formation of CH. But there will be a side reaction also. In the side reaction, their rearrangement occurs and a 5-member ring gets converted to a 6-member ring, and all of us know that 6-membered aromatic structure is more stable as compared to the 5-member. So rearrangement occur and we get another product, that is 3-chloropyridine. Now comes the reaction with CH3MgPr. This is, what is this? This is an organometallic. Alright, what is happening here? MgPr will attach on this carbon 2. Now on further reaction, we can get different kind of products. If we react this with carbon dioxide and acidified water, we will get carboxylic acid substituted pyrrole. If we react it with bromopropylene, we will get a substituted pyrrole. There is some mistake here. Since this is propylene group, we should have a propyl substituted pyrrole. So please correct it in your notebook when you are writing this. Either write it as a ethyl bromide and keep it as it is, or if you are writing as a propyl bromide, then here in the substitution you will be writing propyl. Alright, medicinal use. Pyrrole is used in the synthesis of drug called glycopyrrolate. It is anticholinergic drug. Anticholinergic is like when the bud colic comes, it is generally related to your stomach. So this drug is used to cure peptic ulcer. All right. Second drug is atorvastatin. This is used to manage the high cholesterol and high blood pressure. Now, from both the structure, we can clearly see here we have a pyrrole, which is substituted. Again, in this also we can see a substituted pyrrole. That's it. Furan will study in the next class, and before that we will be doing the nomenclature of the heterocyclic compounds.